First, just briefly, a little bit of a context of what's going to happen. We first got the object and the requirements, research, background investigation, preliminary design, the concept, construction, and then the different tests that it went through. So the objectives of the devices was sort of started from a white piece of paper. Obviously the requirements for my device were to reduce within the 25-year limit, but obviously hopefully a lot less than that. It must be light mass, so it was for a 1U device, so normally less than 100 grams. Size must be within 0.1U, installed on a CubesaT prior to launch, so it should fit within the requirements of the CubesaT, and also be fairly easy that anyone can sort of bring the device in and link it to their sort of system with minimal interference. And so I went through a design, prototype, and test of this, and this is first a little bit about the background in Cape Town. It's a MPhil in space studies, so it's a multidisciplinary degree, covers things from space law to satellite, and then we do 1/3 of courses and 2/3 from your research paper. Professor Steyn touched on it, so I'll just go over this briefly. There's obviously a growing concern about space debris and a growing concern that one CubesaT has become part of that problem. So we're looking for these solutions, and that was pretty much the reason for this project. Maybe what you didn't touch on, this is from St. Louis University, and it looks at all the different CubesaTs, and this is a database that's constantly updating, so this is obviously sort of frozen in time. And you can see the sort of hockey-shaped curve beginning to form with CubesaT, which is beginning to hopefully predict that small space is really now beginning to reach becoming commonplace, and it's going to hopefully rapidly keep on growing. What is important here is, obviously you can see commercial finally start picking up source satellites in the red there, and that 39% of all CubesaTs are 1U, and that of all the launches in the past are 1U, and that's why it was designed for a 1U system, also with the idea that it can sort of be scaled fairly easy to a 3U system. So again, because it was from a white paper, I first needed to decide what the target cross-section area would be. So I looked at different starting orbital heights, assuming a sort of a perfectly circular orbit, and different surface areas. And then from there, I got a range of heights and a range of thingies. So you can see, for example, a normal CubesaT at 600 is sitting for 25 years, which is obviously already beyond the 25-year practical limit. This is all using STK. From there, I did another sort of calculation, and I had to pick between what would be my suitable target of my surface area. I chose 0.06 meters squared because it does 700 kilometers, and by 800 kilometers, both it and 0.1 meters squared are no longer sort of acceptable for the 25-year limit. This is just all the orbits, and this is the typical parameter of CubesaT, where the average CubesaT is sitting, using all of that sort of database, and that's why it's something that can deorbit 700 kilometers. CubesaT seem 700 kilometer orbit to the CubesaT seem quite suitable. And then just to note, for this project, there are obviously slightly different parameters that are entered in, the start date, etc., and that brings the deorbit time of 6 years to my sort of surface area of 0.06. So where does this fit in on all different devices, all different boom devices? So you've got all these different sort of deorbit devices. Mine's a boom supported film cell, and it's a shape memory alloy boom. There's obviously inflatable booms and residual strain booms, etc. Mine's shape memory alloy. This was the preliminary concept. I spent obviously quite a bit of time working on different designs, etc. And this is the sort of final concept that I picked. Basically a housing with a hole for the sail to fold up into, a nitinol spring. The sail gets deployed by a nitinol frame, and it's a gore shape, and it's parabolic. This is how it would fit in a CubesaT. It uses a little bit of the unused volume that sits between the feet of CubesaTs. So because I know now that it was going to be an offset from the CubesaT body, and it was going to be spherical shape. There was obviously a risk between gravitational gradient torque and aerodynamic torque. So calculations were done to ensure that at the heights that this was going to be effective at, that it would orientate itself in an aerodynamic orientation, not in a gravitational gradient orientation. That obviously has severe impacts to the surface area that would see, the velocity, and thus the time for deorbit. So it's very important that it would orientate itself in this aerodynamic orientation. To do that, basically these are the different torques. Obviously calculations were done, and it shows that anything sort of under 700 kilometers is fairly comfortable, and even under 700 kilometers is comfortable that the aerodynamic torque will prevail, and so therefore that's the orientation it should fall into. And then from there, obviously, as it gets closer and closer to the ground, the aerodynamic torque really gets stronger and stronger. So two of the materials that I used are Kapton and nylon. Kapton is the Kapton 50 HN. Low outgassing is an advantage. It's space certified. It's laser cuttable, electrically insulation. Good sort of temperature ranges, etc. Very common space material. And then nitinol has been used before. Nitinol is a mixture of nickel and titanium. It's reprogrammable, so once you set its shape, you can apply a current or heat to it, and it will retake the shape that it's remembered. I'll show you how that sort of setting process works. The one disadvantage is this rhesus effect, which means that basically over time it won't regain its shape as effectively. So you can scrunch it into a ball and drop it in boiling water, or however you want to reprogram the shape by running the current through it. It will be able to take the shape less and less effectively each time. This has got implications, as I'll show you later on, testing the regime, etc. So for the housing, this was the housing. This is the final design of constructed prototype housing. A couple of interesting points here. This is a groove for burn wire release mechanism. I'll talk a bit about the release mechanism in the next slide. Its height is 0.08 U, so below there's a central well for where the sail sits, and there were guiding holes for the lid to ensure that the lid would sit correctly and wouldn't sort of shake too much. And there were pins on the lid to insert into these pins. So how I fabricated the sail. Laser cutter had to design the shape of this core to ensure that the diameter needed to be 28 centimeters, which would give you the 0.06 meters squared. I went about and did that, and therefore the gore, half of these are the 8 gores. 4 gores are just simply Kapton, and then the other 4 are sort of have a frame, a nitinol frame, and the frame links one frame gore, one non-frame gore, and that gives support to the whole structure, which is here. How I set the frame, so you have to design a mold for the frames, feed the wire through, heat it up 500 degrees for 10 minutes, and that sort of programs the shape. And finally, what was the circuit? This was the circuit, which was a partial parallel and series circuit for the Kapton, and that had benefits in the sense that it was more reliable than series, but not necessarily half the current compared to a parallel system. So it's a 1.5 current amp, and fairly low energy usage would be required. The nitinol spring, same thing happened. I used I designed a mold, heated it up. This is the spring, the chord length, the target length is 270 mils. That's how much you need to extend by off the CubesaT, and then it could be compressed into about 11 mil height, which was lower than the depth of the cubes, the housing that's this well. So just a couple of things. The housing, and this is a cover plate to cover it. The helical boom. This is the sail, and finally the sail housing lid that fits here in these 4 holes, and obviously holds the sail. I wanted to make sure that at no stage when we were deploying this, that we run the risk of other materials or bits breaking off and increasing debris. That was obviously a concern. So how about the integration? We've got the male pin and the female pin, and they plug into each other. These are the two bits you couldn't see. So the lid bloom housing, this is effectively a device. It screws into the lid, and then the nitinol wire comes in there, the nitinol helical boom, and that ensures that the boom and the lid are securely connected, because you didn't want to run the risk where the lid would disconnect from the boom, because that would obviously mean that the sail floats away in space and becomes more free. This is simply a ring with 4 holes for screws, which is where, or nuts and bolts, which is where how the nitinol sail connected to the lid. Finally, the release mechanism. I tried and I failed to do a pin and pull release mechanism. There was just a fundamental flaw. The nitinol is too elastic and it was putting too much pressure on the lid. So the pawls using this spring at least wouldn't release the pawls. The force needed to guarantee that the pawls would be released was too great to guarantee any spring that could fit into this tight space. So I basically tried to keep it simple, and I had some help sort of problem solving this, and we came up with the spring and cable solution. So how this works, you have nylon which wraps around these 4, and it gets pulled tight. It's a single nylon thread that wraps around it. And there's the wire on the outside. The wire has a Nicron burn wire that's soldered in at these 4 points. This is a bit of a hack, because this probably wouldn't survive the vibrations of launch, the Nicron. So the solution for future models, which I talk about, would be to have a chip ring on the outside. And that would help. There are definitely ways of making this a lot more secure, but that was the solution that I came up with for this prototype at least. 128 grams, the completed one, and then here's a picture of it being deployed. I'll run you through a bit of the simulations. These are some simulations done on SolidWorks. What's important to note is that here and here, these are obviously buckling risks, because it's sheet metal. There would be, the lid would be supporting it here, which isn't covered in this simulation. And then here, the sail's fairly compacted to this space, and that would be supporting this lid. So the cover plate and the lid are supported in the places where they're buckling the most. And there's actually, these are heavily magnified. There's no real risk of buckling for the housing. In fact, it was probably over-designed. This is the testing rig and how it was tested. It was tested on an airbag to simulate microgravity. Some preliminary tests, I'll skip over these, but basically just how the nitinol was tested, how 1.5 amps was chosen using pulse width modulation, and then right at the beginning just testing that it would work for a paper sail before I used Kapton and carried on with the design. So preliminary test of the release mechanism. So here it is attached, and then you can see it sever and burn there. Is it reliable? Well, it only needs to burn in 2 out of the 4 spots that it's connected to release. Here it is without the Kapton, and then there it is close to show the Nicron wire wraps around the nylon. The helical boom test. So this was a test to release the airbag was activated, so this can freely move in any direction. Current was applied, 1.5 amps for about, I normally, in my calculations, I use 2 minutes, but I found it never took longer than 30 seconds at room temperature. Obviously, I never tested it in thermal vacuum, so that might have a different heating impact. And it elongated to 27 centimeters within 30 seconds. And then from once it's been elongated to 27 seconds, you have to obviously test the sail, so then connected the sail and deployed the sail. This is a picture of the sail, sequence of pictures of the sail deploying. And then that's the sail once it's fully deployed. You can see that mechanism there is 28, sorry, that distance is 28 centimeter diameter. And the height's about 14 millimeters to get the half spherical shape. I did this multiple times to test, and as you can see, the hysteresis started to kick in, which started to affect how the sail could fully deploy. So this device can't be released and brought back in multiple times. It obviously wouldn't be in space, but the testing regime needs to be worked out as such that you don't test it more than it needs to be. And this was tested up to 15 times before you could really see that on the 15th test, the frontal area was only 0.045 meters squared. And then the length was only 24.5 centimeters. This is just kicking in with the material. So the final budget, here's the final dimensions, all within sort of CubesaT dimensions. The power budget, you can see it's got a very low energy usage, and all sort of sections of it are very low. The mass budget is 128 grams. I anticipate the next version to have much lower housing mass. There's a number of iterations which I'll chat about now that could reduce that housing mass quite substantially. And then finally, the cost budget was done. The total project was only less than $1,000, and the prototype cost was $500. So yes, there's a number of tests that need to still happen, but at the moment it's run on an extremely low cost sort of philosophy. So it could do the 25-year-old Deorbit, and it could passively provide aerodynamic stability to the CubesaT. There's low interference with any antennas because it's obviously away from the system. There's potential to increase the radar cross-section, which brings the ability for emerging space nations to track their own CubeSats. Capton would have to be changed to a metallized Capton in that case, but that's still possible. And then, I'm not an antenna engineer, but it's a metallic device in a helical shape, so there's definitely potential for the sail to become an antenna, which would obviously probably greatly, or it would increase the antenna to what current antennas have. And then redesign version 2. So if I was to redo this, what would I do? Obviously the bird wire mechanism was designed for a pin and pull, the groove, so that could hold means that could be changed. Like I talked about earlier, you could have just simply a board with holes in it for the nylon, and these holes can be heated, a bit like Nikon coated, and that will be ensured that the nylon cuts. That will just get basically a simple thermal cut on a circuit board. That will be a lot more effective than this current bird wire that's being run around. I never had any problems with the reliability, but I didn't shake it, so I'm pretty sure that if it gets shook, there would be risks. Then you could also machine out the housing, change the aluminium to the correct aluminium, and anodize it. Substitute the nylon to welcome if you want, drill ventilation holes, insert the camera, design a sail connection board so that there was some finicky connections for how the actual sail connected to the other board, to the lid, and that could also be improved. And then improve how the Nikon cable is secured. I have the copy, it's in my pocket, so I'll just pass it to the judges and you can have a look. This is the final. Thank you.
Thank you, Jim, for your presentation. Some time for question. Did you look at the dynamics between your spring sail and your main satellite? Is it stable? Will it damp over time, or can it go into an oscillation causing problems and breakages?
Yeah, so it's a very good question. As I came further along the project, I realized that there would be perhaps a potential of releasing this maybe even at the beginning of life, which could cause other issues in terms of the fact that you couldn't then point to attitude control, but then you could guarantee that it was deployed to answer the question, what happens if power runs out, etc. So then I started to think about these sort of things. Does it oscillate? Is there damping? I predict, yes, there will be oscillation that would have to be dampened because the sail will never deploy perfectly in a perfect spherical shape, which means that there will always be some slight imperfections on the forces on the sail, and that will cause oscillation. So my solution to that would be a magnetic damping that could definitely still fit in the device.
Just the last question. You designed obviously for the 25 years. The 25 years is the maximum. So if you want to reduce your deorbit time, let's say to 1 or 2 years, what will you do? Just increase the size of your sail at the back?
At the moment it's doing. At the moment it's pretty well under the 25 years. It's about 6 years. So there are different heights. So for R1, for
for the 560 kilometer orbit.
It's 6 years for that. But
And if you want to reduce it,
you could increase the sale, but then you might have to increase the housing, which obviously is more less.
and it is scalable, you can easily do that.
Yes, yeah, you just need to increase the housing.
Why you need AC power for thermal cut?
Why do I?
AC power instead of DC power.
No, it was DC. Sorry,
Ah.
that was a mistake.
Okay. How do you keep the shape of the foil?
The shape of the
Foil.
coil.
Foil. After deployed. After deployed.
So after deployment using the nitinol, so the nitinol frame was memorized in there. So that is it's perhaps a bit difficult to see, but that's actually very similar to this shape here. And so the nitinol remembers that. So when you fold it up and then deploy it, the nitinol will regain the shape once current is applied through it, and will remain in that shape for the duration of its life.
Is it stable under the temperature range?
Yes, they are different. This particular nitinol, this exact one used, I struggled to find the exact specifications, but nitinol has a mix. It's obviously nickel and titanium, and by playing with the percentages of the 0.45% and 55%, you can make it stable under space conditions.
Any other question?
Just maybe I missed it. Do you have redundancy for operation of the system?
So you're talking obviously about deployment?
Yes.
At the moment, no, but there's enough space, I believe anyway, in that housing that in a further addition you could install its own batteries or a capacitor even to charge from the CubesaT from the solar panels and then discharge, because it has such a low energy usage to deploy. So at the moment there is no redundancy. I didn't really look too much. It definitely can be put in, but I didn't go so far as to try and install. I thought about it, but I didn't install the operational how you sort of start.
Just comment. Did you conducted some experiment in the vacuum chamber or something?
No, we don't.
I think you should conduct, because in a vacuum environment, the required power is a little increased.
It will increase. Yes, you're correct about that. So all of those powers are from room temperature, but they are very, very low. It still is quite low. So we're hoping that in vacuum it won't be many multiples.
Is there any other question? Okay.
Hi James, I just want to know, do you have any information about the stiffness of those wires after deployment? How stiff are those wires, and if you get aerodynamic pressure, won't the sail deform? How stiff is the wires?
Okay, so I don't have the exact specification on me now. I actually have it on my computer, but the sail won't deform under the force from aerodynamic pressure. It's not great enough for that usage. Until perhaps maybe at sort of 50 kilometers, but by then hopefully it's burnt up. So.
Okay, any other question? Okay, let's thank our presenter again.